Hello students, welcome back to the classroom point. In our today's class, we are going to discuss about the metal activity series and also competitive electron transfer and applications of the metal activity series, how we are going to use in the both redox reactions as well as in the stoichiometric calculations. So let's begin the class now. So the competitive electron transfer or metal activity series along with its applications. So usually whenever redox reactions we are going to see, or this is also applicable to the electrochemistry as well. So when metals are added to the another type of the metallic solution and some reactions automatically happens. And how could this reactions happens and which metal replaces the another metal, that depends on the activity of the metal. See, the more active metals, they can release the electrons more easily. When they are releasing the electrons more easily, that means they are acting as a strong reducing agents. So that more active metals release electrons very easily and act as the strong reducing agents. And also by releasing these electrons, these metals are going to add these electrons to the other metallic ion, which is able to take these electrons, and that metallic ion must be of the belong to the less active metal. So let us see how this electron transfer are going to take place by taking some examples. So here the point is, more active metals release electrons readily and act as strong reducing agents. And one more point is, more active metals can replace the metallic ions belongs to the less active metals from their compounds. So let us see what are these more active metals and what are these less active metals, and how to remember this metal activity series and what are its applications. So here the metal activity series is, we can memorize this one as P, S, B, C, magentile, TL, and CHAP, CHAAP. So what is the notations of these letters? So this notation says that P stands for the potassium, S stands for the sodium, B stands for the barium, C stands for the calcium, M stands for the magnesium, A stands for the aluminum, whereas Z stands for the zinc, I stands for the iron, N stands for the nickel, T stands for the tin, whereas L stands for the lead. So here we can take the C stands for the copper, H stands for the mercury, A stands for the silver, another A, gold, and another one is platinum. Cost of the metals gradually increases. Copper, silver, gold, and platinum. And in between here, there is a hydrogen. Since hydrogen do not belongs to the metal category, that's why it is not included in the metal series. Anyhow, in applications, we need the help of the hydrogen, and we shall see those also now. So, how to use this metal activity series in understanding these 2 points? Very simple, that these metals are arranged in the decreasing order of their activity. That means potassium is more active than sodium. Sodium is more active than the barium. Barium is more active than the calcium. Calcium is more active than the magnesium, and so on. Then what means? That means potassium can release electrons more easily than the sodium, and sodium can release electrons more easily than the barium, and like this. That means more the active metals, more easily it releases electrons, so that it is acting as strong reducing agent. Less active the metal, it has only option to accept those electrons and to get reduced. So that let us see here by taking some examples. So we shall take zinc and copper. So imagine here copper sulfate solution is taken, to which we added the zinc. So it gives zinc sulfate plus copper is deposited. So here it is, what is the oxidation states of the copper? Copper oxidation state is +2, sulfate -2, zinc is 0. Here zinc is +2, sulfate is -2, copper is 0. So what type of reaction took place here is, zinc converts into the Zn2+ by releasing 2 electrons. Then who accepted those 2 electrons? Copper. Cupric ion Cu2+ converted to the Cu. So that here Cu2+ took up those 2 electrons and finally reduced to the copper metal. So here zinc is making the copper cupric ion to accept these electrons and also get reduced to the copper metal. Means here if you see this side and this side, here also, here copper sulfate, zinc both are in the same solution, but zinc replaces the cupric ion from the copper sulfate solution and converted. And the final solution contains the zinc sulfate and copper, but a reverse reaction is not possible. That means copper is not able to replace the Zn2+ ion as the zinc. Why? Because the electron releasing tendency of the zinc is more than the copper. That is the reason why zinc forces the copper to accept these electrons, but a copper cannot force the zinc +2 ion to accept the electrons. That means here, see here zinc is the more active metal, copper is the less active metal. So that more active metal replaces the ion, this is a cupric ion of the less active metal from its compound, and it occupies its position, and the metal ion which is replaced completely gets reduced. So for this reduction process, zinc is responsible. That's why zinc is here called as the reducing agent. That means more active metal release electrons and act as a strong reducing agent. Then how to understand this one? By testing this zinc sulfate and copper sulfate. So let us take the one beaker in which take the copper sulfate solution, copper sulfate solution. This copper sulfate solution is blue in color, and to this add the zinc metal strip. Copper sulfate solution is taken and we added the zinc metal strip, and finally after some time you can observe that the solution completely becomes colorless. And whatever the zinc strip we have taken, that zinc strip started slowly getting coating of the red color. So from where this red color was obtained, that means whatever the copper deposited, this copper starts depositing on the surface of the zinc metal strip. That's why this red coating has obtained. And here copper sulfate now changed to the zinc sulfate solution, which is colorless. Zinc sulfate solution. So it has no color. color is completely changed. Then how to test whether zinc sulfate is present or copper sulfate is present in the final solution? Very simple. Just try to send the hydrogen sulfide gas, H2S gas, through the final solution. See here, if zinc ions are present in the final solution, then this Zn2 plus reacts with the sulfide ion and forms zinc sulfide, which is a white precipitate. If copper ions or cupric ions are present, that cupric ions also react with the sulfur to form the copper sulfide, which is a black precipitate. But in this reaction, when final solution is tested with the hydrogen sulfide, black precipitate is not formed, but white precipitate is formed. That means no amount of copper ions, cupric ions are present. All cupric ions are completely replaced by the zinc. That's why only zinc sulfide white precipitate is going to obtain. And you have to remember one more important thing, that copper sulfide is very less soluble in the solution. That's why its tests are very sensitive towards the H2S. Even very micro quantities of copper is present, that immediately react with the hydrogen sulfide and giving the copper sulfide black precipitate, and black precipitate can be visible very easily. Even no particles of the black precipitate is formed. That means all cupric ions are completely replaced by the zinc ions, so that finally copper only present in the form of the copper metal. Okay. Now here, if you consider the zinc and copper, so that we can understand that zinc is more active, copper is less active. Zinc is the more reducing agent compared to the copper. Now let us take another two elements, that is copper and silver. Let us take the example. When silver nitrate on reaction with copper gives copper nitrate solution and silver gets deposited. In this reaction, let us see the oxidation states of the metals. Here silver oxidation state is +1, copper is 0, NO3 is minus. Here copper is +2, NO3 is minus, silver is 0. So here copper reduces the Ag plus ion into the Ag, and reverse reaction is not possible. Why? Because if it is reverse reaction is possible, then silver also has to reduce the Cu2 plus into the Cu, which is not possible, because the electron releasing tendency of the copper is more than the silver. And here, how to identify whether the reaction is proceeding towards the product side or not? The silver nitrate solution is a colorless solution, and a copper nitrate solution is a blue colored solution. And moreover, when we add hydrogen sulfide to the final solution, copper ions reacts with the cupric ions, react with the sulfur to form the cuprous sulfide, which is a black precipitate. So this confirms the conversion of the silver nitrate by the copper into the copper nitrate and silver. Now let us take another equation which is not mentioned here, only nickel is mentioned. Let us take the cobalt and nickel combination, in which Ni2 plus ion means nickel solution, nickel compound reacts with the cobalt and giving CO2 plus and nickel. An interesting thing in this reaction is, at equilibrium, we can identify both the presence of the Ni2 plus and CO2 plus ions. That means the electron releasing tendency of both nickel and cobalt is almost nearly same. That is the reason why neither of the ions gets reduced or neither of the compounds metals gets oxidized. Both can coexist at the equilibrium, so that if you test for the CO2 plus ion, you will get the positive test, as well as for the Ni2 plus also we get the positive test. So that it shows that both are having the equal tendency in the releasing of the electrons. Now, what other information we can gather from this series? it clearly shows that, see, the hydrogen is placed here. The metals which are placed before the hydrogen, they are all more active metals, and they can liberate the H plus ion from the, that means acid solutions. Let us take an example here. Zinc plus HCl. See, these metals can replace the ion of the less releasing capacity element from its solution and deposit as the respective compounds. Now here, zinc oxidation state is 0, hydrogen is +1, chlorine is -1. Zinc can replace the H plus ion from the HCl solution and liberate the hydrogen gas, and finally here, zinc chloride and H2 gas is released. Means whatever the metals are placed before the hydrogen in this series can liberate the hydrogen gas from the acids whenever they react with the acids. That means the electron releasing tendency of these metals is even more than the hydrogen gas. So that's why hydrogen gas cannot be used in the extraction of any of these metals for the reduction process. Now, what about these metals? The metals which are placed after the hydrogen in this series, they cannot release the hydrogen gas whenever they react with the acids. If you take the copper with HCl, no hydrogen gas is released. But copper releases hydrogen gas only with the HNO3 molecule. It is not because of the H plus ion, it is because of the NO3 minus ion. NO3 minus ion can oxidize the copper into the Cu2 plus. Now let us take here. So copper plus 2 HCl. Reaction is not possible. So in HCl, H plus ion is present and copper. So the electron releasing tendency of the copper is less than the H plus or hydrogen gas. That is the reason why even if copper releases electrons to the H plus ion has to convert in the hydrogen. But hydrogen has the more releasing capacity than the copper. That's why again reverse reaction happens. But whenever you are using the HNO3, it releases the H2 gas because of the oxidizing power of the NO3 minus, and that is nitrate ion. Now let us see how to use these metal activity series in solving the stoichiometric calculations. Usually in the stoichiometric calculations, we have to follow these certain reactions. If you don't know the reaction and the product and completely reactants and products and how the reaction is going to take place, it becomes difficult in the calculation of the mole-mole relations or the mole-mass relations, whatever the type it may be. So let us see how this metal activity series helps us in identifying the reaction, certain type of the reaction, so that we can easily identify the complete reaction. Let us see that now. So I am writing here PS. We know that what is meaning of PS. P stands for the potassium, S stands for the sodium. So this I am taking as one set. Next one, PS, BC. These are all Magin, TL, C up to here. What is the meaning of this? Barium, calcium, magnesium, aluminum, zinc, iron, nickel, tin, lead, copper. So this is one set. And next one is HAAP. So meaning of this one is mercury, silver, gold, and platinum. So let us see how these metal hydroxides, carbonates and nitrates responds to the thermal decomposition process. So in thermal decomposition, both the potassium and sodium hydroxides and carbonates do not decompose. That means, for example, if you take Na2CO3 and try to heat it, no product is obtained. So these hydroxides and carbonates are so stable to the heat that they do not decompose. Then nitrates, both potassium nitrate and sodium nitrate. When heat, they give the nitrite plus oxygen. So let us take NaNO3. On heating gives NaNO2 plus half mole of the oxygen. So oxygen is a gas, so that in stoichiometric calculations we can easily identify the products. Now let us see with these compounds. Barium to the up to copper. Hydroxides. These compounds hydroxides. On heating gives metal oxide plus H2O. Carbonates. On heating gives metal oxide plus carbon dioxide. Nitrates. On heating gives metal oxide plus NO2 plus O2. So let us take some examples here. Calcium hydroxide. When you heat it, according to the equation, you will get the calcium oxide plus water. And carbonates, let us take magnesium carbonate. When you heat it, we will get the magnesium oxide plus carbon dioxide. And nitrates, let us take the zinc nitrate. On heating gives zinc oxide plus nitrogen dioxide plus oxygen. We have to balance the reactions now. So here, by using these general methods, we can easily identify what type of the products are going to obtain. And remember that these nitrates, metallic oxides are all in the solid state. Rest of the byproducts are in the gaseous state. Now let us see the last part of this one. That is these metal hydroxides. On heating gives metal plus H2O plus O2 oxygen, whereas carbonates on heating gives metal plus CO2 plus O2. Nitrates on heating gives metal plus nitrogen dioxide plus oxygen. Let us take an example, silver carbonate, Ag2CO3. When silver carbonate is heated, it gives silver plus carbon dioxide plus half mole of the oxygen. As I said earlier, so metal activity gradually decreases, and one thing we can observe that these two metals are highly active. Since they are highly active, they do not want to release the elements that are present along with them. So they are always want to be present in the combined form. They don't want to dissociate. That is the reason why here these will not dissociate, and in this case still they maintain the rest of the sum of the compound with them. Only some amount of the oxygen they are releasing. But in this case these metals are little bit less reactive than them. That's why, and more reactive than these metals. So that is the reason why these metals, whenever you heat, these metal compounds, whenever you heat, still they maintain oxygen along with them. See that metal oxide is still present, and remaining non-metal along with non-metal element along with the oxygen is slowly released. And these metals are very less reactive metals, and moreover we can see that silver, gold, platinum, these are almost treated as the noble metals. That means they don't want to combine with any other element. They are always available in the native form. Native form means only elemental form directly from the earth crust. So that means these are very less reactive metals. They don't want to be with any other element. That is the reason why whenever you heat their respective compounds, they completely lose all elements with them and finally converting into the metal form. See that all metals are formed, remaining non-metals are released. So using this type of the equations, we can easily guess what is the products in the reaction. For example, 10.6 grams of Na2CO3. 10.6 grams of Na2CO3 on heating gives how many moles of carbon dioxide? So if the question is asked like this, people usually guess that carbonates decomposes and giving the carbon dioxide. That is not possible with all the elements. For example, here I had given already. Carbonates do not decompose. So sodium carbonate do not decompose. That is the reason why we get the 0 moles of carbon dioxide. Similarly, some X grams of silver carbonate on heating gives how many moles of the carbon dioxide? That means, see, we have to write down the balanced equation like this, so that you will get the carbon dioxide. Even oxygen also, if asked, we can calculate it. So using this short tricks, we can easily identify the products in the reaction, so that moles calculation also becomes very easy. I hope you understand this video. We shall meet in the next video. Thank you.